All right, this is a sound tube right here, and we are basically going to create a harmonic. Now we're going to have water inside the tube here. There's going to be water up to a certain level. That is going to be the fixed end, and this is going to be the free end right here. So, I'm going to play various frequencies, and we're going to try to figure out where the harmonics are. So this is 1,000 hertz. Now, as I pour water in, I'm going to pour water into this reservoir right here. And the water basically is going to fill into the tube to the same height as that. So water is being poured into there. It's now going through the tube and filling up here. Water is going to rise until the water on both sides are the same. Water level is now here. And I might have to go get some more water. That's going to be an exciting part of the video. So recognize that I can change the level of the water in the tube here by just moving this up and down. Sorry about that. I might have to mute that part of it. So as I lower the water level here, notice the water level here is dropping. Yep, you can see it. So it's dropping down. Or as I raise this, the water level in the tube goes up. I'm going to need a little bit more water. I want the water to get closer to the top, so I'm going to pause it here. So I've added water to the tube, playing 500 hertz at a low enough sound because I need to be able to hear the resonance. So what's happening is the sound wave is traveling down to the top of the water here and then bouncing back. So as I raise the level of water here, notice there was a point where the sound got a lot louder, and that's because as sound was traveling down and bouncing back, it was interfering with itself. We get the loudest sound when we get the antinode up here of the two sound waves vibrating back and forth, because the antinode is you have a lot of pressure pushing one way than another way. So basically, at the antinode, that's when you get the most extreme in pushing, and that's when your eardrum vibrates the most, and that's why we hear the loudest sound. We want to be able to figure out what the height of the water here is. Now, we do have a centimeter measuring scale along here, and a piece of tape, and it starts 2 meters below the top for some reason, and I never quite figured that out. I thought I had a reason for it at one point, but that doesn't seem to have held true. So whatever measurement we get along here, we're going to add 2 centimeters to it from the top. Somewhere around 13 centimeters. All right, so definitely pass it down here. So that was about 13.1 centimeters on here, plus the extra 2 centimeters, so 15.1 centimeters gets a resonance. That would be the first harmonic. Now the next one should occur at 3 times the length. So if that was at 15.1, so 3 times would be 45.1 minus the 2. So it should be somewhere around here that we should get the next harmonic. And in case the water overflows here, I have an extra cup here to quickly dump into it, and I'm hoping that I don't soak the carpet. Let me put extra protection down here. All right, So we are going to try this again. It's looking like 46.2 centimeters on here plus 2, so 48.2 centimeters. So let's try it again with a different frequency. That was 500 hertz. Let's try 400 hertz now. Notice that the first harmonic was indeed a lot stronger than the third harmonic. Slightly different tone there. So let's get it back up here again. Water level is rising. Oops. Oh, there's a kink. There's a kink in the tube keeping the water from rising. All right, so let's take it up a little bit farther here. There's definitely a strange sound right there. That is actually not the harmonic. That is, I believe it's due to the width of the tube. The first harmonic really should be the loudest. Right there. So 17.4 centimeters plus the 2 at the top, so 19.4. I expect the next harmonic to be down here somewhere. Again, that's a false harmonic there. That can really mess up the data if you take that into account. So it's about 59.8 centimeters on the 2 plus the extra 2 at the top. Let's go to a different frequency here, 300 hertz. That was it right there. .6 on the scale right here, plus the 2. And the next harmonic should be down here somewhere. False harmonic. And I'm having trouble identifying it. There are a lot of sounds there. The question was that it there? Or was it up there? So about 27. 27 times 3 makes it 81. Now this is a one lab where you shouldn't calculate and then go to your calculation, but it really is helpful to know where to expect it because there are a lot of sort of what I generally refer to as false harmonics. So that's 81.2 plus the 2 centimeters, 83.2. And let's go to a different frequency, hopefully one that can be heard better. Let's go to 600. So 9.2 centimeters on the scale here, plus the 2. Man, having a hard time finding that one. So about 36.8 on the scale. Should be able to find a third harmonic here. That's the third harmonic right there. Somewhere around the 65 centimeter mark. And let's get a fifth one. I'm going to go 700 hertz. 9 centimeters plus the 2. Man, having issues here. So I'm going to scrap that because I'm not quite sure how much more will be gotten out of that. Let's get this set up. You're about to hear screeching metal on metal. I guess I could have stopped the video first, but I didn't. And now we will go to the plot, find out what happens. When we're dealing with the harmonic with one free in and one fixed in, there's another video where I go through the math, but basically for the first harmonic, the length here is equal to a quarter of a wavelength. I know that the speed is equal to frequency times wavelength, or wavelength over period. The wavelength here is equal to 4 times the length of the air column, and so this becomes 4L times T. Since length right here, or height as I have in the spreadsheet, that length is equal to 1/4 VT. And so therefore, if I'm plotting length or height times the period, or versus the period, I should get, ideally, it should be linear going through the origin here, and that's the slope. I put this into y equals slope x plus b form. So my intercept is 0. My slope is 1/4 v, and that's the speed of sound. And so the speed of sound should be 4 times the slope. When I'm looking at the next harmonic, which is known as the third harmonic, where that is my height, that's equal to 3/4 of a wavelength, and this is why it's called the third harmonic, because it's 3 times that. And so the wavelength is 4/3 times the length. So similar math over there, V is equal to 4/3 the length over the period. Solving for the length, we have length is equal to 3/4 VT. Again, that's my y, that is my x, and so therefore that is my slope, and my intercept is 0. So the slope is equal to 3/4 times the speed of sound, and so the speed of sound should be equal to 4/3 times the slope. And that's the math that we went through. So I input the data into the spreadsheet. I have the temperature, which if you look at the other video with the hollow tube, you'll see how I came up with that speed of sound. I input the data that we had and came up with a slope. We actually look at a plot of it.